on totally a different day, if we're looking at chiral molecules, how can we actually verify before we ingest them? So we talked about them having different properties, but how do we actually know that what we're about to eat or drink or really anything or give to somebody else is pure or has some chirality associated with it? So this gets to a technique known as optical activity or optical rotation. And so it turns out that chiral molecules interact with light differently, but we do have to make sure that that light allows us to see that interaction. And so what we're seeing here in that image is kind of how it's set up. You take a lamp, a sodium light, right, because that emits a very singular wavelength. You pass it through a filter so that you make sure that you're only getting that wavelength of light, because that cleans up some of your interactions. And then what we're seeing with that diagram or that little spinny wheel there, it's not really a spinny wheel. What that's saying is that that light is now moving all directions. Okay? And what we're then doing is passing that through that filter. Well, the point of that filter is to go ahead and change how the light interacts. Okay? So what it's going to do is take all of those other directions that the light is moving and remove them. Okay, so that we get only a singular kind of direction or plane on which the light moves. And for those people being like, there's glasses, if you've got fancy and now it's less fancy, but polarizing sunglasses are doing exactly this. Okay, and a fun little observation to prove how well your polarizing sunglasses work is if you take two glasses that are polarized and you take their lenses and you turn one 90 degrees and overlay them, what you'll see is that no light passes through. Why? Well, the first one removed the sides, the second one is now removing that last axis of light. Right? So polarizing filters do exist. We use them in our sunglasses. Now the light is aimed on that one plane, and now we pass it through our sample. Right? If our sample is indeed chiral, what will happen is it'll just kind of tick the light, turn it a little bit. The more times we impact chiral molecules, the more it rotates. So then what we can do at the end of this is just put another kind of lens on this where we would look in and we would just rotate that lens until we saw the light. Okay? That means we would now have a way to monitor how chiral it was by a degree readout. Okay? And that's the point of that kind of degree readout is we would then say, oh, it rotated light X degrees. Right? And we could note that in either a positive direction or a negative direction. Right? That positive and negative, of course, we can't use the terms positive and negative because they're used for everything. So we invented a term, and that would be levorotatory for rotating it light to the left or negative direction, and dextrorotatory for rotating light to the right or the positive direction. Okay? That is then symbolized in our name as negative and positive. So you might have seen, say, a compound written out as, I don't know, let's call it negative ibuprofen. Let's do naproxen because I don't remember if ibuprofen was chiral or not. And I do remember naproxen. So we could have negative naproxen. That gives us information that when we looked at the naproxen, we knew it was rotating light to the left. Right? That's kind of that point. That's what we're saying. Right? Which is nice. Right? So we know that we now have that. What does that mean back to the S and R that we've also identified? Right? So S and R were ways that we could label that naproxen. We could call it S naproxen or R naproxen. And one of them was dangerous and one of them wasn't. Right? So do those tie to the plus and minus? No. Okay? And that's a bit unfortunate. Okay? But R and S are an interpretation of the structure, the drawing. Plus and minus are an interpretation of the output, right? An experimental output. So plus and minus really have no bearing on R and S. Sometimes they overlap and they're the same. Sometimes they're different, right? Which means don't associate minus with S and plus with R, even though we're talking about left and right, right? They're different things. Okay? So be careful with that. The next thing I'll point out or mention that you may see in future classes, particularly if you're taking biochemistry, is you may see reference to a capital L and a capital D. Think level rotatory. No. Capital L and capital D are a biochemistry way of analyzing carbohydrate molecules and based off of the structure, not experimentally. Okay, so capital L, capital D, also way different than level rotatory, dextrorotatory, negative, positive, R and S. All different systems for all different purposes. Okay, you might also see a lowercase l and a lowercase d. Those do reference level rotatory and dextrorotatory, so they do overlap with our plus and minus. Those happen much less frequently, just because we already have the plus and minus system for that. Okay? I know, confusing, but that's the system that we work with. So from our polarimeter, we can now get these numerical values. Those numerical values can give us some information. Remember, as we talked about this, we're going to encounter some issues when we're looking at that sample. Okay? Remember, I said that as the light comes in, if it impacts a molecule, the light rotates. Okay? Well, what if you have more molecules? If you have more molecules, well, the light's going to rotate more. Right? That shouldn't have an effect on the absolute kind of rotation of our sample. So what we need to do is take a way to convert the output from our spectra or the output from our instrument and normalize it. Right? For people being like, God, normalization, that's awful, percent yield is a normalization process. Right? That's what we're looking at here. If you think back to Beer's law, absorbance equals BC epsilon, that's a normalization process. You're taking into consideration the other variables that will contribute to the output of your signal. Right? So when we look at this individual experiment, what we're going to get is an observed rotation. That observed rotation, we have decided to say is affected by our concentration of our sample, which we just addressed, and the path length. The longer that path length, the more likely we can encounter molecules and the more likely we can get a rotation, right? Before we get that output. And so that's why those things get factored in. We don't want to report an observed value, just like you wouldn't report that I got 0.5 grams out of an experiment, out of, say, a recrystallization. And you're like, well, 0.5 grams, that was more than you started with. Well, you're only referencing that because of the lab experiment where you started with 0.1. If I started with 50 grams and I got 0.5 grams, well, that's not a very good yield, right? So we don't want to look at the observed rotation. The observed rotation needs to go through this normalization process, and what we end up evaluating is what is known as the specific rotation, right? The specific rotation is the useful one, and that's the one we would use to analyze and see everything else. Okay? The exact concentration or the calculation of the specific rotation is not something I would ask you to go through and do. It is something in second semester, assuming we get to run that lab, I would have you just run kind of a test calculation on it because it's a little bit weird things, and you're seeing that with the value of concentration. You're doing grams of compound per milliliters of the solvent. It's a little bit of a weird system, but you just run the calculation and you get your specific rotation. Well, what can you get out of the specific rotation? Okay, well, the specific rotation we can actually kind of put into a formula to get us, more importantly, the EE. Well, what did we say EE was? That was in our last video. That's the enantiomeric excess. Okay, so how much I got out of that sample. To really understand that, we have to go back and think about what we would get for our different enantiomers. If we started this system off where I had, say, pure R, okay, so one enantiomer that's pure R, okay, the only direction the light's going to rotate is according to that enantiomer. Okay, so let's just say For giggles, it rotates it to the negative direction. Okay? So we would get an output, let's say negative 10 degrees. Okay? And we'd run our calculation, and that is our specific rotation. Well, what would happen if I take now a sample of pure S and I put it in? Same compound, but now S versus R. Well, enantiomers interact as mirror images. Well, what's the mirror image of the negative? Positive. And that's exactly what happens. So if we now take that pure S, it rotates to the positive direction. Well, how much should it rotate? Well, it should rotate the exact same magnitude as the R, just the opposite direction. So in this particular example, we're saying one enantiomer rotates positive 10, the other enantiomer will rotate negative 10. Right? And that's their kind of range, which is cool. What if we had a mixture? Well, if we had a 50-50 mixture, half of our sample rotates positive, the other half rotates negative. The net result is no rotation. Right? We would get zero rotation of the light because both molecules are flipping it back and forth. Neat. If we have, say, a slight excess of one, right, now we're not going to get quite as much rotation, right, as the pure, because there's some of the other enantiomer causing the light to rotate back. And now what we're seeing is how that could get affected into our enantiomeric excess. And so what we're talking about here in this formula is that we would typically take some unknown and we would observe its rotation. Okay? We would compare that to a standard that was pure. Okay? If our unknown, when we did this ratio, came out to be exactly the same as the pure, well, then we know our unknown mixture, quote unquote, was pure. If it was different, well, now we know that there's a shift in or a mixture within that of a little bit of positive, a little bit of negative, and they're not perfectly, or they're canceling each other out, preventing some of that rotation. That allows us to come up with that expression of the enantiomeric excess equaling our mixture over our pure. And then I almost always forget to multiply by 100% when looking at percentages, but there it is. Okay? So if we remember from the last video, enantiomeric excess also had another equation. Okay? That enantiomeric excess, we said, was the percent major minus the percent minor. Okay? And that was our enantiomeric excess. So what does this mean? Well, I have now two equations. With these two equations, I have the potential for solving for an unknown variable. And it turns out we actually need a third equation in this, and we'll see that in just a second. In fact, I believe that second is not yet, but we'll see that in a second. So the big bottom line I want you to really be able to evaluate is this concept of optical activity. Right? So if I look at these 5 things, I want to know, should they show optical activity? Well, if I have a compound that is, or a mixture that is just the R enantiomer, yes, I should have optical activity. Right? Is it positive or is it negative? That was a bit of a jerk question, right? Because it's not positive or negative. I don't know. It could be positive, it could be negative. There's really no good answer to that. I would have to test it to see what the result was. Right? B, a meso compound. Oof. Well, now we've got to pull back all those definitions in that last unit and say, well, what was a meso compound? A meso compound, when you went through and did it, had an internal mirror plane. So if we looked at a quick structure of this, wedge, this would be a meso compound because there was an internal mirror plane. Right? Well, does that show optical activity? Well, is there chirality behind this? And this becomes the biggest aspect that I really should have defined. Our optical activity is really just telling us that our solution is chiral. Right? So an R enantiomer is chiral. Right? There's chirality there. Well, a meso compound does have chirality. It has chiral centers. But is the molecule chiral? Right? That's a harder question And no, the molecule is not chiral. It's actually achiral, which then means optical activity, it shouldn't have any. Could we see that? Well, if we bust out our nomenclature behind this, for this position, priorities 1, 2, 3, we're going, if I'm doing that right, counterclockwise. That's clockwise. So I would assign that as R. Helps if you can get your rights and lefts figured out. 1, 2, 3. That's now counterclockwise. That position is S. So light comes in, sees the R, rotates one direction. The light continues to pass through, sees the S, and rotates the equal but opposite direction, canceling the rotation of the light. So an achiral compound, okay, note, achiral compound, the molecule, will not show optical activity, okay? But a chiral compound will. Okay? That does not mean there's no chirality within the molecule. It just means the molecule itself is achiral. Kind of a challenging concept. You're looking at the molecule versus atoms. Optical activity is the molecule. R and S is atomic analysis. If we move to C, an enantiomeric or a mixture of enantiomers, 1 to 3. So 1 part S, 3 parts R. Well, yes, this is going to rotate light. Okay, so let's go through and see if we can come up with some guesses on what we might expect out of this. Okay, let's say our R enantiomer, because we said that was a yes, this one was a no. Okay, let's say the R enantiomer rotates positive 10. What would I expect? Because this is not an equal mixture, so that solution is chiral. There's an excess of the R. What would I expect the rotation to be? Okay. Well, if the R was positive and the S was negative, I have an excess of the R, okay? Which means the optical activity that comes out had better be positive. Whoops, as I try to underline that, it should be positive, okay? Should it be greater than 10? Well, no, 10 was the pure, so it needs to be less than 10. Okay? So the exact numerical value, you could go through and calculate. I'm not going to calculate, but I'm going to guess that we're coming in at about positive, whoops, that's an eraser, positive 7. Okay? So it should rotate significantly to the right because there is this big excess of our R enantiomer. Okay? So you could needle through some multiple choice questions, because we could tell you have this 1 to 3 mixture, and you could see a negative 10, a positive 10, and maybe a negative 7. Okay? You don't have to run any calculations. We know the negatives don't make any sense because that says S is the excess. Okay? Remember, we're given this information also in the question. Okay? Positive 10 would be pure, so it's not that one. That has to be our answer. So you can work through this without running calculations. And I want you to kind of keep that in the back of your mind when you go through and solve these things. How about a mixture, another mixture of enantiomers, where we have 1 to 1, half R, half S? The solution is achiral because we had both of those pieces in there. It hits R, rotates one direction, hits the S, rotates equal but opposite. So not what's the word? Not optically active. Last one on the list, a mixture that has a 0% enantiomeric excess. Okay? That means there's no excess of one over the other. Oh, that's the same as D. That's a 1 to 1 mixture. Yep, it is. Okay? In that 1 to 1 mixture, we would then again say no optical activity. Okay? Just to summarize that all out, we said yes, yes, and then the rest of these were no's for no optical activity. Okay, so there are a variety of ways we could ask this. I'll throw in F, and what comes after F? G, okay, a chiral sample or an achiral sample, so we can throw in some extra words. A chiral sample is going to be yes, optically active. Achiral, no, optically inactive. Okay. You'll note that we've got 1, 2, 3, 4, 5, 6, 7 possibilities here. This could come out as a really easy which of the following shows optical activity, select all that apply in an exam question. Just kind of thinking through things out loud. Okay. Last part, we could go through and run a calculation. If you don't want to do the calculation, that's okay. I fully understand and appreciate that. I don't want to do it either, but for those people that are interested, we'll have to go through and do it. So specific rotation, 2s iodobutane is plus 15.9. We want to know the percent composition of an enantiomeric mixture of 2 iodobutane. So I have a mixture. The rotation of that mixture is this negative 3.18. Okay, so how would I go through and do this? Well, the first thing I could go through and do is say that the enantiomeric excess was equal to mixture negative 3.18 over positive 15.9. Okay, this is going to be weird because if we did this calculation, we're going to get a value that is negative. Okay? How do we have a negative enantiomeric excess? I thought the enantiomeric excess was always the highest minus the lowest. Well, that just means you didn't look at your system or think through what those numbers meant. If you're getting a negative value for your mixture, which enantiomer do you have? Well, you don't have the S, you actually have the R. So what we could go through and do is change that to a negative. Okay? This is going to help us to analyze our end result. I also don't have a calculator immediately handy, which makes this calculation a little bit more challenging and time-consuming, which is fantastic because we're getting recorded through this process, and I'm really now just wasting your time and mine as I try and go through and run the calculation in a calculator that took a little bit of time, but there we go. We get an enantiomeric excess of 20%. And 20% what? Right? Well, we could call it 20% minus, or we could call it the 20% R. How do I know it's R and not S? I thought we said S and the plus and minus system was different from the R and S. It is, but I've already established that S is positive. Okay? The question told me that. Right? So now what can I go through and do? Well, if I know the enantiomeric excess is 20%, I could go back because I know I'm going to multiply by, let's not do that. I could say 20%, this equals the percent of R, because we said the R was the one in excess, minus the percent of S, okay? Well, how is that going to work out for us? That's going to be a bit wonky. How would I solve that? I don't actually know what the percent of R or S is. I just know I have an excess of R. Well, there's another equation that you do actually know. The percent of R plus the percent of S. You're like, how would I know that? Well, there's only two possibilities, which means your total percent is, oh snap, 100%. There it is. Okay? So now what could I go through and do? I can say the percent of R is equal to 100 minus the percent of S, and I could now go through and do a substitution. The percent of R, we said, was 100 minus S minus S. This was still 20. And now I could run my actual solve all the way out. I get minus 80 equals negative 2S, or we get S equals 40, which means my R equals 60. Okay, and there is my percents for that end result. Right, that would allow me to do that solve. Note, the math really isn't difficult. Maybe dividing the fractions are, but we could process through some of that. If this showed up on an exam, you could go through and run the calculations, but I would also probably set it up so that you could reason through your multiple choice answers and eliminate all but one. Okay, so with that, we're done with the calculations, and really the big concepts that I want you to get out of this. S and R versus plus and minus. They are unrelated. Do not start associating S with plus and R with minus. Okay? That relationship has to be defined in the information given. So remember back to this question, we knew S was plus because we were told that information. That wasn't something I knew coming into the question. Okay? If S is plus 15.9, then R must be minus 15.9. Okay, then pure R must be 15.9. Okay, and that relationship we know to be true because the S and R are opposite. And then the last big one here, that plus or the percent S and percent R must equal 100%. Okay, so those are our big concepts. Hopefully that made sense. I do apologize for running 5 minutes in that stupid calculation that I should have prepared better, but we've now at least covered all of our optical activity, and we don't have to stress about it again, but we will have to stress about spectroscopy, which is our next sequence of videos. Thanks for watching.